Well, hi, hello. Welcome to section number 5. We have our little QR attendance code up here. So I think the question of the day is, so how are you feeling about the exam? Yes, and actually I've set aside like the first like 10-ish minutes of section to be like, so what do y'all think of the exam? How are you feeling? So does anyone want to kick us off with their feelings on the exam?
I thought the mechanism was tricky.
It was.
Yeah, that's the one that I feel like I had the most trouble with.
Yeah, it's one that I think that the difficulty of the mechanism in this exam was definitely harder than practice exam 1A, but not maybe as hard as 1B. Like it's kind of somewhere in the middle.
Yeah.
I did think of that one, and when I did, I was like, ooh. Mostly just because I think it had some cute things in it, you know? Like, cute thing 1, she's kind of like a hemiacetal, kinda, but then just a little spicy. And then, cute thing 2, she had a thiolate attack. Ooh, ooh. When we kicked this off, this now is an S- that can do a 1-4 addition. And then the third thing I liked about her was there was this other dangly bit over here, which after a few more steps, she started to form a new hemiacetal. And so it's kind of things that y'all have seen, but stacked in a weird way. And just, yeah. And I think the other thing that made it hard is just it's so many rings and everything, right? Yeah.
I know what's your practice B video. I want to have you know to do like a video really fast. I watched the practice B video when you did the maximum right before, and then it made sense once I asked broke off.
Ding dong. We're out here. Yeah, I recorded that like the day that I wrote all the exam questions, and so it was just in my head. Yeah, other thoughts and feelings about the exam?
I thought I did the synthesis right until like I got to like the group exam and I was like, well, I messed it up.
No, that's valid. I pitched several different versions, so I pitched 3 versions: a simple version, moderate version, hard. We did a kind of like we changed around some carbons, but we basically did the moderate version here, where essentially you had to do the 1-4 addition first. And again, the carbons on this are not what you all saw in the exam, but it's the same kind of idea. And then what you had to do was you had to use NABH4 to only react with the carbonyls, not react with the ester. That makes these into 2 alcohols. And then this, you can cap it off with a carbonyl to make an acetal. And now she won't react at all. So then you can react with the ester, do whatever you want. So it's kind of tricky because normally you think of carbonyls being protected by turning them into acetals. And like this is the carbonyl that went into the acetal, but actually we need to make it into the alcohol that went into the acetal. So that was the tricky part of it.
So
Yeah.
who like did it in a different order? Like,
Well, I mean, I can show you a draft. Like, I did a draft that we were doing, and I did it in 4 steps, and I realized I could break the synthesis that I wrote by just, like, I could circumvent. Oh, wait, this is something different. Yeah, that's one of the practice exams, sorry. Yeah, I was doing this, and I was like, I could just reduce all of this and then get an acetal. And so we had to add some things to make that like not as viable. You would still get partial credit essentially. Yeah.
What happens if for the mechanism like you did extra steps? Like you did unnecessary protonation.
So the mechanism is the only question I'm not grading. And I made a deal with Logan. I said, if you will grade the mechanism, I will grade the other 8. Just because y'all are new with reactions and the things that y'all try to do on the first exam mechanism are really upsetting. So I'm going to let Logan make the judgment calls on that one. But generally speaking, you get points for correct arrows structures. And so, like, if you started off good and then went off the rails, you get points if it started off good. Yeah. Other thoughts of that you were about to share, right?
I didn't like the 4th box problem that there's like 2, 1, 4 connected.
Oh, that was tricky. That was tricky. That was the trickiest box problem by far. It was this one right here, right?
Yeah.
Yeah.
Because I genuinely tried to find a way to do 1, 3 grab.
Well, and that's the thing. We can't, if we're doing box problems, we can't give you tricky mechanisms. They have to be standard reactions, just like you would see in like lecture notes. And so, yeah, no, that's the trickiest. That's the hardest thing on the box problem page. Yeah, and we try to have like one box problem be kind of gimme points, one be hard, and two be moderate. This was our hard one. This was our gimme one of just like a simple enone of like just add two things to the enone. But even like our easy questions are not. Like you still have to think a little bit with it, or you still have to know it a little bit. Yeah. Yes.
On the Newman projection one, was it safe to assume that like the R in between the two other like
Is the least stable.
Mm-hmm.
Yeah. But now we're asking like content questions about the exam. I'm more concerned with like how do you feel about the exam? Like maybe can we do like some thumb meter responses? Like, do you feel like the format of the exam was comparable to the practice exams and you knew what you would be tested on? Okay, work. Did you feel like the exam was significantly harder than the practice exams? Like, if you felt like the exam that we gave you was harder, can you do more of a thumbs up? And then if you feel like it was just like way easier, thumbs down, about the same, middle?
It's like in between.
Felt it was harder. Tell me more.
Like the one curveball that like I didn't expect was when we had like the acid one, and like we had to use like the conjugate bases because we never really practiced
Yes.
using conjugate bases and like PKAs like that.
You're totally right. Like, that one was harder. That was like 4 points out of the 150. And it's something that like in previous years, like 2019, 2020, we asked that a lot more. And then we stopped asking it for a while, and I was like, that's a good question. We should ask that. And so it was either that or like ranking base strength. Y'all have seen one thing that's connected to it, which is an extra challenge problem is covered on, like it does the base. But like, yeah, if I saw that on the test, I'd be a little bit like, that was a little dirty, but fair. Other like thumb question. So, do you feel like the challenge problems in practice exams helped prepare you for the real exam? It's okay to show dissent. Like, I want to hear, cool. Like, I guess what other resources would be helpful for you? Because, like, the practice exam solution video, that was something that I recorded this year because it was on the midterm feedback last year. And, like, we have videos for exam 2 and the final practice exams. But, like, given that you've now seen the first exam, like, what materials do you wish you would have had? Or, like, what would have been helpful?
I would say just like extra mechanism like box problem and like synthesis like practice.
Yeah, I hear you. So it's a tricky thing because we have more practice exams that we could release. And the reason we didn't is mostly just because, like, y'all, we imagine we're working on the problem set until Monday and then had 2 practice exams that we want you to do pretty thoroughly. Like, that, again, taking like 8 or 9 hours on Tuesday and Wednesday. And I feel like if we give more practice, it incentivizes you to get through the practice as fast as possible rather than, like, go through them thoroughly and, like, try to learn from it that way. It's kind of like, oh, okay, if there's so much, I can just, like, plow my way through it and eventually I'll get it, rather than, like, figuring out why things were missed. So it's kind of the balancing act that we've gone back and forth about that. I'm going to try to do a little bit more, like, extra practice before exam 2. So there'll be some extra practice problems released. But I think what I'm going to do is I'm going to release them, like, the day before. Like, if you finish the practice exams, here are some extra problems. But if you haven't, do the practice exams. Yeah. Another suggestion I got in the 8 a.m. section was videos talking through the challenge problems. Like, potentially. Especially, I think it would be helpful for, like, the box problem mechanism synthesis kind of ones. For the theory ones, like, it's a little bit more, like, hit or miss. Yeah. You're catching us, Summer, at the towards the end of our discussion of the exam. Do you have any thoughts about the exam? So real for that.
Let's talk about you talked about it. So
Yeah.
It's fine.
Okay. Cool. Yeah. Mm-hmm.
I just have to think like I knew there was like Wednesday office hour, but like for the Monday office hour, I don't know why in my mind I thought it's gonna be so much more like exam help room than like
Yeah.
problem set. And
I mean, you also had a problem set due that night. Yeah.
yeah, so I was like maybe like before like when we go like to the final exam or like midterm two because there's more content, it's like if there is more help room other than like the day before the exam because it just
Well, we were a little disappointed because in the help room the day before, there were like not more than 5 people there. Like it was real. Like there was a whole hour where there were like 2 students.
it's just because it's the day before of the exam. Like, it's just like everyone's like just doing their own things. And then if I don't,
Yeah.
if you don't understand something at that point on Wednesday, you just leave it there.
Okay, I hear you. So, but then I feel like our only other option is do it Tuesday, which half of y'all have lab. So like we can do it Tuesday night. Like I will be here from 6 to 9 p.m. on Tuesday. Like is that going to be more preferable than doing it just the day before?
I think Wednesday helps for me.
The day before.
Instead of Tuesday, yeah.
Maybe we'll try to split it up. Like maybe Logan will do his on Wednesdays and Wednesday, and I'll do mine on Tuesday, just so that there's a little bit more variety. Because I totally like if I was a student, if there are office hours the day before, I'm not going because I'm in like panic, like lockdown mode of like
Yeah.
gotta do my studying. Yeah, so fair enough. The biggest thing that I would encourage you to take with your exam score, which you're gonna get your scores back on Monday evening probably. It's feedback on how well your studying has prepared you for the way that we are going to test you. It's not feedback on like can you do organic chemistry or not, or like what your final grade is on the class is going to be. It's how your current study methods for the first exam prepared you for the way we tested you. And we are going to be testing you in a very similar way for test 2. And so really I think a lot of it's going to be feedback of like what is and isn't working with studying. I'll have more information about it next week, but the week before the second exam, so in 2 weeks from now, I'm going to be doing meetings with all the students, like one-on-one meetings, and they're going to be like 10-minute meeting slots. So I'll release a whole big calendar, and you can sign up for anywhere between like 1 and 3 slots to like go through and talk through some of the specific study strategies. I'm also going to be talking more about like how to study reactions. Part 2 and 3 is coming up. So just keep an eye out for it. There will also be a process for regrade requests and some detailed announcement about that as well coming your way. But let's pivot into section materials. So if you haven't already, scanning the QR code. And the game plan for today is we have 4 big topics. So we have amines and enamines, we have redox, we have CAD reactions, and we have amino acid chemistry. So I'd like to try to get through some of the challenge problems of these. So we're going to just jump into it then. First off, we have the amine and enamine family here. So previously we have seen CO double bonds as a carbonyl. And we also talked about this compound functional group, the enol, where we have an alkene and an alcohol. Together she's an enol. Well, if we take those same ideas and make them nitrogen, then we get our new functional groups. So a CN double bond is called an amine. And then if we have an alkene right next to an amine, it's called an enamine. Enamine, like enol. The other thing that came back was in one of the earlier sections, I talked about naming or classifying nitrogens, or classifying amines, I guess, as primary, secondary, or tertiary. And that's according to how many carbons are attached to the nitrogen. So like here, this is a primary amine. Here, this is a secondary amine. This is a tertiary amine, something like that. And then we have some like side players, but we'll get into that once we all talk about the reactions. So our first kind of core reactions for this family are the synthesis of amines or enamines, which we make by taking ketone or aldehyde and adding either our primary amine or a secondary amine. If we add a primary amine, we are going to wind up with an imine. and all of these sound the same, right? Like all the functional group names sound a little bit the same. The thing that I would say is primary, if it's only one carbon on it, then we can keep our CN double bond. But secondary, if we react with a secondary amine, then we have to form this little side enamine bit. And we'll see why in the mechanism in a second. For these, we also sometimes put like pH of about 5, but I don't think that we're going to actually require you write that. So, both mechanisms for forming amines or enamines have the exact same first 4 steps, and then they differ in their last step. First off, the lone pair of the amine will attack the carbonyl. When we do that, we're at a tetrahedral intermediate here. And then we do our proton transfer to make everything neutral. So we're going to add an H onto this O and remove one over here. Now, this neutral structure is called a hemiaminal. And I was on this floor of Science Center when I first heard that word. I was in a lecture hall, or not lecture hall, like a review hall over there. It was a review session for a test. And the TF said hemiaminal. And in my head, the only thing I could think was Gesundheit. Of like, that's an involuntary utterance. Hemiaminal, what are you talking about? That just like fell out of your mouth. That's not real. What game are we playing? Hemiaminal is organic chemistry being like so aggressively on its bullshit that like I can't anymore. And now here I am saying hemiaminal. So the hemiaminal is this stable intermediate in the reaction, and it's stable because it's neutral. And so typically whenever you're doing these mechanisms, you're going to form the hemiaminal. Okay, well let's see where we're going. In order to get from our ketone aldehyde to the amine or the enamine, we have to kick off this oxygen somehow. So next thing that we do from our hemiaminal is we protonate the OH, make it a good leaving group with water, and kick it off. And then we get to this aminium ion. So aminium, it's just like an imine, CN, but we have a positive charge on it. And so I put these up here as the side players of hemiaminal and aminium. Yeah. So once we are at this is the point where it matters. Did we start off with a secondary amine or a primary amine? So if we started out with just a primary amine, then there's only one carbon-based thing on our nitrogen, and the other one's a hydrogen. And so we can just finish off the reaction by deprotonating at the nitrogen, and it makes our neutral amine. We're done. But if we start off with a secondary amine, that means that our nitrogen is attached to 2 carbon groups. And so we don't have something easily on the nitrogen that we can deprotonate and make it neutral. So instead what we have to do is we have to go next door. So there is this nomenclature where if we have a CO double bond or a CN double bond, if you kind of circle the double bond and go 1 carbon over, we call that the alpha carbon on either side. And you could keep on going out. 2 carbons out is the beta carbon. And we call hydrogens on an alpha carbon alpha hydrogens. And hydrogens on a beta carbon beta hydrogens. This will come back in like lecture 10, but it's useful to have language for this right now because we're about to be doing something with that. So when we get to this aminium situation down here with a secondary amine where we can't deprotonate anything on the nitrogen, that's where we look next door and we ask, hey, alpha carbon, can we remove one of your hydrogens to get a neutral charge? And the alpha carbon's like, oh, I don't see why not. And so our solvent can come along and do an alpha deprotonation. So it's going to grab the hydrogen on the alpha carbon, push in and push up. And we've seen this like a little bit before when we were doing conjugate addition. So in conjugate addition, we'd get to a point where it would look like this. Like we've added our new thing, and we have this double bond CC and an O minus. And we said we push down and we grab a hydrogen, and the hydrogen adds at this position. This was an alpha protonation, and now we're doing an alpha deprotonation. It's, again, just kind of looking next door for our hydrogen being added or removed. So, again, amine, big thing is whether or not we have primary or secondary. That determines which fate. They have the same mechanism up until the last step, and it's just differing where we take off a hydrogen. So these are the formation mechanisms. And we also want to know the reverse of these. These are reversible. So in order to go from an enamine and an imine back to a ketone or aldehyde, you need to use H3O+. The reason why you need to specifically use H3O+ and not another like acid is because you need a source of oxygen. Like this oxygen that's going to be in the product ketone or aldehyde came from like an H3O+ or H2O. Here, I'm not going to go beat by beat through the mechanism because it's just the reverse. Like in the forward direction, we said the last step was different, and then all the initial steps are the same. Here in the reverse of the reaction, the first step is different, but then everything else is the same. There is one typo I want to just point out because ChemDraw just doesn't like me. ChemDraw is the notation typesetting thing. There's an extra H that's just put there for no reason, and that's on the hemiaminal structure for the reverse. And I had already proofreaded this. I made this nicer than like last year's, and ChemDraw just said, you can't have nice things. Here we are. Yeah. So with this, what I'd like to do is I'd like to look at a kind of difficult question with amine enamine that's on the problem set. It's on a skill builder. I think it's page 8. Yeah, page 8. So this one's pretty tricky as a mechanism, which is why I wanted to talk about it together. But first, let's do our kind of analysis of the line reaction to try to give us hints for our mechanism. So what functional groups do we start off with over here? Aldehydes. And then what type of amine do we have? Primary or secondary? Primary. Only one carbon. So we have a primary amine and we have aldehydes. So is that going to make an imine or an enamine normally if you just had that information? Imine. So let's just draw what that imine should be. So the fake mechanism for the imine I think is really easy. Literally it's just like drag this and put the nitrogen to replace the O and then erase a hydrogen.
It doesn't attack both?
Like hypothetically it could, but I'm just saying like what's an easy first step that we could do.
Oh, okay.
If we see in the product we only have one nitrogen, so we know that both of them were not attacked in the same way, or they weren't attacked by different ones at least. Yeah. Cool. So I'm going to give y'all 2 minutes, and I want you to actually write out the curved arrows to get here. So these are going to be beat for beat, arrow for arrow, the exact ones that are right here. You're going to have your amine attack, you form the tetrahedral intermediate, proton transfer. You protonate it. Then you do a lone pair push, kick off water, and then you just deprotonate the aminium. So take a minute to try to map this onto that question. And actually, I'll even put this up here so that you can be like writing it and like look at it as needed. Hannah decided to abandon y'all today. Wow. Sent her a text being like, so we noticed you weren't in section. This is always the section that has the worst attendance of the whole summer. Because everyone's like very hurt after the first exam, which is valid.
We don't have
Yeah.
to draw arrows for proton transfer, right?
Correct. And maybe one thing I'll point out is proton transfer is very specifically one deprotonation and one protonation. So you couldn't write proton transfer and go directly from here to here. Because when you do that, you have 3 hydrogens that are moving. You're adding 2 here and removing 1 here. So proton transfer is only add 1, take 1. Okay. Are we at the imine? Okay. So, now let's pick up and do the harder part. So that part was like just straight up what was in lecture. But then from here to here, we need to figure out what's going on. So are there any atoms or like key structural features that could help you map this intermediate onto the product? Like, are there any atoms where you're like, I'm pretty sure this in the intermediate is this in the product? The methyl and the anion, both. Excellent. So this methyl nitrogen is probably this methyl nitrogen. Okay, well in that case, let me call this carbon, this like blue. And does it matter which side I put it on? Oh no. Could have been so much worse. Could have been so much worse. Wow. Honestly, a blessing. God's real. Here we are. I fear. So this blue carbon is going to be connected to the nitrogen. Over here, does it matter which side we assign it to? No, they're exactly the same. It's symmetric. So we can just pick one and we say that's going to be that carbon. But then we have kind of two boring carbons and we have a green carbon, right? So we have like two boring green carbon. So if we do that, two boring green carbon, it seems somehow we need to get our nitrogen attached to the green carbon, the same nitrogen attached to the green carbon. So to do that, we need nucleophiles and electrophiles, right? Well, our green carbon aldehyde that we have in our current intermediate, is that a nucleophile or electrophile? Yeah. This aldehyde green carbon, is it a nucleophile or electrophile? It's an electrophile, right? Like in all of our reactions from lecture 3, we attacked this. So, if we are making a bond, we need a nucleophile and electrophile. If this is the electrophile, then the nitrogen has to be the nucleophile. So this is the weird step that y'all have not seen before. In order to get to this product, based on this mapping that we just did, we know that this nitrogen has to have that carbonyl, and hey, that nitrogen has a lone pair. So we are going to have our imine attack the carbonyl, and that's the new step. That's the thing that's weird, wonky, and wild. So now, when we do that, we are attacking within the same molecule, so we make a ring. And so I'm going to show you one tool that I like to do, which is just numbering. So what I'm going to do is I'm going to number 1, 2, 3, 4, 5, starting at the carbonyl C. And I know I'm going to be making a 5-membered ring, and one of those atoms is going to be nitrogen. So I don't even think about it. I write a pentagon and I put a nitrogen on one of the corners. And then I can start mapping it out together. So I can do 1, 2, 3, 4, 5. And now that I have my number system keep track of things, I can just ask, okay, what's on each thing? Like on 5, on the nitrogen, we need a methyl. On 4, we have a double bond here. 3 and 2 are boring. And then 1 should have what on it?
Oxygen?
Yeah, an O minus. And anything else we're missing in the structure? Formal charge?
Yeah, for the carbon on one, for the nitrogen.
For the nitrogen.
Okay.
Because this carbon on 1,
It has hydrogen.
yep. So again, I think this numbering tool is really, really helpful when you're doing an intramolecular reaction that makes a ring. Okay, so now we need to figure out how to get from this thing to this. And already I'm seeing some charges. So let's deal with our charges first. We are in like neutral, mild acidic conditions. So let's just protonate this. And I'm just going to write H plus. It could just be like water that's being deprotonated, but it's a protonation, so we're not going to think too much about it. Now, we have a positive charge on a nitrogen. Can we deprotonate that nitrogen? No.
But we could
So-
deprotonate the hydrogen.
Yeah, our strategy last time where we were trying to remove a positive formal charge on nitrogen and we couldn't deprotonate it was look for the alpha position and deprotonate there. So it's a little bit weird because we're on a ring. But here, this is our imine. So our neighbor alpha position is next door to the carbon. It's over here. So let's do an alpha deprotonation. Work. So we're starting to look like our product, right? Like we have one of our double bonds in the 5-membered ring. We have a ring. What are kind of remaining things that we have left to do in order to get to our product? Yeah, we need to kick off the auction and we need to make another double bond, right?
Should we do the same thing?
Something like that, something like that. So let's look at the functional groups here. We do have an enamine that we just made. But then what would we call this if we have an N with some junk and an OH? Hemiaminal comes back. It's always there. So remember, our hemiaminal was we had an OH and we have N and some like R groups on it. That's an OH, that's N and some R groups on it. So this is an intermediate like halfway through the imine formation reaction. That's her. And hey, we had a strategy already where we protonated this and then did a lone pair push, kicked off water. And we're trying to remove water. So let's try to just map that on to these 3 steps right here. So, first thing that we are going to do is we are going to protonate our OH. Let's see. Hemiaminal. Then, we now have OH2 as a good leaving group. We lone pair push from the nitrogen, kick off water. And now we yet again have a positive charge trapped in a nitrogen. We can't deprotonate it, so where do we look? We look at the alpha carbon. So now our N double bond C is here. We look one next door to the carbon. So this is our alpha carbon. So we are going to do an alpha deprotonation here. And that will take us to the product. So, long mechanism, there's a lot going on. Our product is weird, wild, and wonky. But of this, all of the steps that led up till here were the imine formation. This was the one weird step that we had an imine attacking a carbonyl instead of a normal amine. And then after that, the steps that we had here were we are going to do an alpha deprotonation from an enamine. And then this was like half of the reaction of the amine formation where we protonated our OH into water and then kicked it off. So I think the hard part is not specifically the steps, but how to like figure out what is going on and how to map it on what you've seen in lecture. And that is mostly just a skill that's coming with practice and consistently doing these strategies of like comparing your intermediates to the products, asking yourself what bonds need to be made and broken. Yeah.
Just a quick question for the formation of the amine.
Mm-hmm.
Because it's NH2, do you just deprotonate last step, or do you do like the double proton transfer?
When you say double, like, do you mean just proton transfer? Or?
Like, is the proton transfer for both of those H's?
Like, in the Ford mechanism, like.
Because that's NH, NHR2. But we
Mm-hmm.
had the NH2.
Yes, and it's because like here, this I'm just drawing it out one way. Like this would be a secondary amine, or if it was a primary amine, you would have one R group and two hydrogens. But the thing that we were adding was a primary amine, so you're still having a hydrogen on here.
Yeah, I'm saying like kicking off both hydrogens, like it's first you do the proton trans. Is it like?
You left your phone, didn't you? Yes, feel free to go get it. Like, it attacks, and then first one of the hydrogens is leaving in the proton transfer. And then, if I look at the structure here, the last hydrogen leaves in that last deprotonation step. So, like, right before this, it looks like this.
Okay, yeah.
There, that's what you're talking about. There you go. Took me a second. Cool. Okay. Well, that's amine, enamine. Let's move on to a new family. Let's talk about some redox reactions. Now, in Gen Chem, you probably did stuff with oxidation numbers. Do y'all remember that? There were lots of like formulas, like oxygen always has 2 minus, and hydrogen's always +1. Organic chemistry, we don't do that. We say we only care about carbon, and let's call it the oxidation level to make it easy. We need a just shortcut way of like looking at a carbon and seeing what its oxidation level is at. And so our oxidation level is just how many bonds to electronegative elements do we have. So the highest oxidation level that we can get is 4, because carbon makes 4 bonds. That's going to be like CO2 or carbonic acid here. Oxidation level 3 are carboxylic acid derivatives, where they all have like a carbonyl and a bond to something else. But then also interestingly, nitrile with 3 bonds to N fits in here. So the nitrile in the CAD family does very much feel like this meme of like Power Rangers, and then hi, here I am. So oxidation level 2 are ketone aldehydes. Oxidation level 1, alcoholamine acid, alkyl chloride. The reason why we do these like oxidation levels is because functional groups that are in the same oxidation level do similar reactions. So like lecture 3 was on oxidation level 2. Lecture 5 is on oxidation level 3. Lectures 6 and 7 are on oxidation level 1. Like we are doing a tour through all of these to figure out their activities. Now, redox reactions are reactions that change our oxidation level. So if we go up in oxidation level, we call it an oxidation. If we go down, it's a reduction. And we have some key players that are going to be carrying out our redox reactions for us. So first up, our main oxidizing agent is chromium trioxide, CrO3. She's also called the Jones reagent. She is from the earth. She enjoys long walks on the beach, and she has sidekicks. So she is always going to appear with one of 2 sidekicks. The first one is pyridine, which is just a general base. The second sidekick is water. And so we're going to have to think about which one to use and in which circumstance. Now, our main reducing agent, you know her, you love her, lithium aluminum hydride. You saw her a lot in exam 1. Maybe I'll just tell her her nickname, LAH. Just because sometimes saying lithium aluminum hydride is far too much, we can just call her LAH. Typically, do not put this down as a reagent, because when you're doing exams and stuff, you want the specific like government name of all the reagents. But LAH can get the job done. So they are going to be doing a lot of work for us, and box problems and synthesis. So this is a little unorthodox, but can we give them a round of applause? Thank you for your work. Wow. Doing the heavy lifting here in our class. So there was a page of lecture where there were a bunch of line reactions where we were like, hey, by the way, all these happen. You don't know the mechanism. Moving on. And so I'm going to talk a little bit more about them, but that's going to be kind of the vibe. Like these, since you aren't required to know the mechanism, these are only going to be for box problem questions and synthesis questions, but they are going to be things that you need to know in terms of just how to write the product and what reagents. So let's start off with our oxidations. So a primary alcohol over here, what oxidation level is it at? 1. There's only 1 bond to an electronegative element. And then if we go to an aldehyde, we're at oxidation level 2. Okay, we just went up 1. Well, B, we're also going from 1 to 2. But then C here, we're going from oxidation level 1 to what's a carboxylic acid? 3. So if we are just going up from oxidation level 1 to 2, we use our oxidizer chromium trioxide and we use pyridine. But if we are going all the way to oxidation level 3, our sidekick needs to be water instead. And the reason for it, like the biggest reason in my mind, is here in the carboxylic acid, you have 2 oxygens now, whereas you initially started off with 1. So that second oxygen needs to come from somewhere, and it's coming from the water coming and attacking. One that we don't explicitly mention here is you could just start at an aldehyde and go straight from to a carboxylic acid. Like if you did an aldehyde, you wrote CrO3H2O, you could get to a carboxylic acid because it's going from oxidation level 2 to 3. The other reason is this is kind of an intermediate when we go from 1 to 3. So if you just started off an aldehyde on some random problem, you could go directly to a carboxylic acid with this. So that's mainly it for oxidation. For reduction, lithium hydride, heavy duty. So you've already seen it reduce like ketones and aldehydes to alcohols. But if we have a carboxylic acid, we said the oxidation level of that is 3. It is going to do almost like an ester double addition and take it down to a primary alcohol. If we have an amide, this is also at oxidation level 3, and we're going to oxidation level 1. And here, it's going to take an amide down to an amine, which is a little bit weird. Like, over here, you're used to just kind of erasing, and then it's the OH. Here, you can do the erasing again, too, and just replace it with H's. But just remember that the nitrogen sticks around instead of the oxygen. And then the last one is a nitrile, and this one's probably the weirdest one of them, where this carbon becomes a CH2 here, and then this nitrogen becomes an NH2. So, I'm going to, give an announcement. Perk up your ears, because this will come back. You are only going to learn 2 reactions in this entire course that make an amine. And those 2 reactions are these. So, if you see a problem where you have an amine as the product, you either did an amide reduction or you did a nitrile reduction. And a nitrile reduction, remember, is only going to give us primary amines because this nitrogen becomes NH2 here. Like, it can't be attached to other things other than that. So, only 2 to make amines. Now, with that, let's look at some box problems here. So, these are from Skill Builder page 6 and challenge problem 3. And I've just highlighted a few of them to do. I'm going to give y'all, 3-ish minutes. Try out some of these, try out 1 or 2 of them, and then we'll go over them together. Be thinking about the redox reactions. Also do kind of functional group analysis of starting materials and products. gonna give y'all about 30 more seconds, and then we'll talk about them. Okay. So, in the first one, what functional group do we have our starting material? Ester. What about product? Carboxylic acids. So, carboxylic acids we know we can make from redox from alcohols, right? So, if we think backwards, let's imagine what the alcohol version of this would be. It would be like OHs on the end. It's almost like we were kind of deleting the carbonyl. Okay. Ooh, well this is like a long chain with O's. And this is all bundled up, but we still have 1, 2, 3, 4 carbons, 1, 2, 3, 4. So this needs to turn into this somehow. Well, if we need to open it up and turn an ester into an alcohol, you've seen that in lecture 3, right? Like we could double add what? We could double add hydrogens. Yeah, exactly. So let's use our lithium aluminum hydride. And we do our double addition, 2 equivalents with an H plus workup. So if we do that, our shortcut for double addition to esters was we cut here to our OR group and we put an H on the other side. The carbonyl we transform into an OH. And then on that carbon or whatever we double added. So in this case 2 hydrogens. And again, that's just the, quote, fake mechanism for, like, how do we draw the product of a double addition to an ester? You look suspicious of that, Matcha.
Yeah, because isn't the ester double addition, the fake mechanism is just replacing the carbonyl with alcohol and then adding 2 H's? That's what it is.
Yeah, that's verbatim what I said.
Yeah, but then now there's 2 alcohol.
Well, because normally, like, if we had this as, like, an ester that was, like, OET, and we did that, we would cut this off, this would become HOET, another thing, and the other one, OH, put the 2 hydrogens. But this is not a cyclic ester. When it's cyclic, she's still connected. Like, this OH is from the alcohol that we kicked off. Yeah. Totally. And now, can you verify that these are the same? Like, I've just written it out differently. But it's an OH, 4 carbons, and an OH. So now, to get to the end, we just need to oxidize it. So if we're going from oxidation level 1 all the way to 3, we use chromium, but what sidekick do we use?
Water.
We use water, because we have to introduce another oxygen into it. Cool. Now, for the second one, what functional group do we have in our product? Product. Yes. So secondary alcohol in the starting material, and then acetal in the product. Acetal is giving us flashbacks to yesterday. So what we can do is let's do our fake mechanism on the acetal because we only know one way to make an acetal. Let's cut it off and then put a carbonyl in its place. And then the thing that we chopped off was this diol. Okay, so we need to get from our starting material to this ketone. So should we use chromium or lithium? If we're going from alcohol to a ketone. Chromium, we're oxidizing, great. So with CrO3, what sidekick, pyridine or H2O? Pyridine. Cool, and that's because we're just going to oxidation level 2, we don't need to add an O. Okay, so now to make the acetal, we just add our diol with H+. We're done. Then last one here, what functional group do we have in the product? An enamine. Work. So we know enamines came from secondary alcohols and carbonyls. So our fake mechanism for it, we haven't really had much practice with it because it's new. But what we do is we locate our full enamine, it's this whole group, and we cut the CN bond that's in there. Now on the nitrogen side, we just put an H, and that part's done. On the carbon side, we don't draw that double bond, we just keep it as a single bond, and then we put a carbonyl on the end of it. And we can see that this enamine, initially there was an H there, so I'm going to also write out the H here just to make the aldehyde look less weird. Okay, so now we have to turn our starting material into this aldehyde. If we're going from an alcohol to an aldehyde, are we doing an oxidation or reduction? Oxidation, yeah, same as what we did the first step before. So we are going to use our CrO3 with pyridine. And now, to form our enamine, we need to add our amine. And you can either just write, oh, that's horrible looking. You can either just write the amine, or you can also write, I think Logan said pH around 5. But, yeah. Essentially, if you see this, don't be alarmed. I don't think that we're going to require you write pH around 5. Yeah.
So this like NH that we just added, is that the equivalent of like the NHR2?
Yeah, that's exactly it. Yeah. Where here, just the R groups are attached to each other.
Okay.
Yeah. Yeah. Cool. So that's pretty much redox chemistry. Let's bop along, talk about some CADs. So, this isn't my most yassified chart, but I did a gentle yassification of one of the pages of lecture. And it's because one of the most important things for you to know about the CADs is the relative stability of them. Like, who is more stable, who is less stable. Of our CADs, acid chloride, we're worried about her. We don't know what she's up to. She seems on the brink. She's going to react with anything and everything. Like, do not press her because she is ready to explode. That's acid chloride, most reactive of all of our CADs. Whereas our carboxylate, they're just chilling. They're doing their 9 to 5. They're like grinding, sticking around with their little resonance. They're chill. Everything else is kind of in the middle. Anhydrides are pretty darn reactive like acid chloride, but we don't use them that much. Esters and carboxylic acids are kind of right in the middle. And then slightly lower are amides, even lower than that are nitriles. And we have resonance reasons to explain all this, so I would say definitely make sure to go through this at some point so that you see all these arguments and you can kind of rationalize it to yourself. But at the end of the day, to work the problems, the big thing that you need to know is just who is more reactive, who is less reactive. So this is a kind of reaction web with all the reactions taught in lecture. Logan, I think, put the chart version of this. I don't know. The web to me is just easier to look at, but you have access to both now. And here, the CAD family of reactions, the shared purpose of all of them is just to interconvert between them. With these family of reactions, there are kind of two big ideas or two key principles here. One, everything can become a carboxylic acid. These are here, 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 and here. Carboxylic acid is the Grand Central Station terminal, the Moynihan train hall, the Atlanta International Airport, if you will. Everything's going through it. So, we can always become a carboxylic acid is big idea number one. Big idea number two is it's easier to go down in reactivity than it is to go up in reactivity. So if you start an acid chloride, the most reactive, you can directly in one step go to an ester or an amide. But if you were an ester and you wanted to become an acid chloride, you cannot go up directly. What you instead have to do is two steps. You have to first go to Grand Central, carboxylic acid, And then from carboxylic acid, you can go into acid chloride. So those are kind of the key ideas that are going to ground you in a lot of these problems. So maybe before we fully turn it over to practice, let's do one together here. So here we have a carboxylic acid, and then what do we have over here? Say again? Yes, y'all all are saying it. Amide. Great. So we have carboxylic acid and amide. Now, which of these is lower in reactivity? The amide over here. So we are going down in reactivity, which means we should be able to do it in one step. So if we go and like look at our little tree, we can go from carboxylic acid to amide using DCC and whatever amine that we plan on adding. So DCC, and then for our amine, let's just chop off right here to see what that amine should be. Well, that amine is going to be this 5-carbon ring, or 5-atom ring here with a nitrogen in it. And we just plop an H on. And we just saw her a minute ago, didn't we? Yeah. No. I'm losing my mind. Anyway, but that's it. Like, we are going down in reactivity so we can do it in one step. Whereas, let's see, this third one, we're going from an ester to an acid chloride. Are we going down or up in reactivity? Up, because acid chloride's the most. So, our strategy is first we need to visit Grand Central. So we can use H3O+, or we could do it in 2 steps, do NaOH and then an H+ workup. That's going to take us to a carboxylic acid. And then we use SOCl2 to get us up to the acid chloride level. So again, that's kind of the way that you're going to want to think about these box problems is, are we going up or down in reactivity? And then you can use your reaction web. Now, you do need to know the mechanisms of all these. You've been taught the mechanisms of all these, but all the mechanisms are really similar. And they use a lot of the same like logic as like the acetal kind of reaction. The basic setup for all of these families are you have a nucleophile attacking the carbonyl, you get to a tetrahedral intermediate, you push down, reform a carbonyl, kick off a leaving group. And the other steps are literally just like protonations and deprotonations, proton transfers. So the main way that you are going to be tested on these reactions, though, is probably through box problems and synthesis. Like, we work with this family a lot more at the line reaction level. Again, it's not to say that these won't come up on a mechanism, but they are primarily tested with box problems and synthesis. So this is the web that you're going to want to get to know pretty well. So with this, I'm going to have y'all work on the other practice that I have on the other page. Those practices are from challenge problems 3 and 4 and from Skill Builders page 6. But I will leave the web up on the screen so that y'all can have it as kind of reference while you're working some problems. And for that, there are like 3 left on the page. I'm going to give y'all like 3 or 4 minutes. Try them out, and then we'll do the rest together, okay? staring down one of the reactions.
I'm trying to figure out what this is.
What functional group is it?
Oh. And
So not quite an enamine. If it was an enamine, the double bond would be right next door. So she's just an amine. And ooh, I set off alarm bells earlier. I said there are only 2 reactions in this entire class. She's gonna come back. The alarm bells won't just go off today.
oh, now it makes sense.
Ding dong. Can't believe I thought you were 30. So let's talk about it. Second one here. We're going from an amide to an ester. So are we going up or down in reactivity? We're going up. On our little web, we have to go up. So can we do that directly, or do we need to go to a carboxylic acid? We cannot. Oh, is oh. Work. Yeah. So we need to go to a carboxylic acid first, and then to an ester, because we are going up in reactivity. So with that, our going from an amide to a carboxylic acid, what reagents do we use from the web? There we go, H3O+. And then to an ester, we need to have our alcohol here. So we are going to chop it off on this side of the carbonyl, and then we get our alcohol. So ETOH, that's her. Yeah, in many forms. Yes, this is the alcohol and alcoholic beverages as well. So we do our Fischer esterification. We have our ester. That one's not too bad. The last one's a little bit weird. Or, no, we have one in the middle. Acid chloride to amine. Amine? Alarm bells, alarm bells. We only know 2 reactions that make amines. Is this a primary amine? No. What type of amine is it? How many carbons is it attached to? 3. So this is a tertiary amine. So there is only one reaction in this entire class that will make a tertiary amine, and that is the reduction of an amide. Work. So now we just need to go from acid chloride to amide, which are we going up and down or down in reactivity? Down. Summer's on. Summer said, let's talk about it. Dang dog. So we need our nitrogen, like we need our amine over here, so we're going to chop that off, and we get nitrogen in a 6-membered ring. Okay. And from acid chloride to amine, there are 2 ways that we could write it. We could write it as just our amine here, and we could write that we have excess, like we have a lot of it, or we could write our amine and put pyridine. Either one works. It's essentially, if we don't put pyridine, then this part of our reagent will act as a base in the reaction, and so it won't do what we want it to do, so we're going to have to add even extra to get our full product. Cool. And then finally, going from the amide to the amine, we use lithium aluminum hydride. We do our reduction. H plus work up. Cool. So in last one, we just take a step at a time. We have a carboxylic acid and DCC HNET 2. If we look at our web, DCC is what helps us go from a carboxylic acid to an amide. Locked in. So, with that, we now have our nitrogen here after step 1, but the nitrogen already had 2 ethyls on it. Okay. So we are at our amide. And then we're doing lithium monohydride on an amide. Well, that's literally what we just did. So we're just reducing it to an amine. And what that looks like is we just need to erase her. So our final product here is this amine, which can be written out as NET3, triethylamine. Which this is related to like a cousin of this structure. Is one of my favorite organic chemistry structurals, which is what if you have 4 of them? Well, then this necessarily has a positive charge on it, and this is the tetraethylammonium man. Looks like a little dude, just vibing, a little dance. Cool. So that's kind of the CAD family. That's the way of thinking about it. Are we going up or down in reactivity? If we're going up, we have to go to the grand central of the carboxylic acid. Down, we can do it directly. And then we're going to intersect it with other reactions from other lectures. So like here, I guess from other families, sorry. So here we did like CAD reaction, then we did a redox reaction together. Okay, last little section, which is on amino acid chemistry. So, amino acids, you know them, you love them, you've seen them in so many bio classes. And they said, well, it has an amino group and an acid group. And now you know that that means it has an amine functional group and a carboxylic acid functional group. At pH 7, we get this Svita ion, where we have a negative and positive charge. We need to know how to make amino acids. That's our kind of first big topic in this. So if we don't have an amino acid and we need to make something into amino acid, we start off with an aldehyde, and then we do kind of a combination of reactions that we've seen up until this point. So we add NaCN and NH4Cl, but these are going to be doing kind of 2 separate things. NH4Cl, it's literally going to do an imine formation reaction with these 2 and form this iminium right here. So that is like the reaction that we saw at the beginning of class today come together, but we're just doing it with like an NH4 plus rather than a primary amine or a secondary amine. And then the new thing here is it's just having a CN minus do an attack of that iminium. When we do that, like this is the one new arrow, we get to this intermediate that's called an alpha aminonitrile, where we have an amino group and we have a nitrile. And then the second and third steps are, second, we do an acid hydrolysis of the nitrile, and that's going to turn it to a carboxylic acid. And then we neutralize it. And we can neutralize it to whatever pH that we want. We can kind of choose the protonation states when we have a neutralization step here. So you could be responsible for this whole like full curved arrow mechanism. Like we could put this as an exam question, do a Strucker synthesis here, and like do all the curved arrows. Much more likely, this is going to be something used in synthesis. So I would not worry about it too much, but I would say at some point for practice, try drawing it out, because these are all reactions that you are responsible for. It's just put together in a very long scheme. So then we have our DCC player. So DCC, you don't need to know her structure or anything. DCC is a matchmaker. It matches carboxylic acids to amines and makes amides, which biologists call peptide bonds. The issue becomes, what if we have multiple OHs, or like carboxylic acids, multiple amines? Like let's say we want DCC to join these 2 together, but it could also join these 2. And like that's the difference between getting this product and this product, which they look very similar, but stereochemistry-wise, they are not. And I could ask you, what's the relationship between all of these? But yeah, now I'm thinking, what's the relationship? These are constitutional isomers. Yeah, because they're attaching different places. You could also have one molecule of this with the R2 thing react with another one of these R2 molecules, and DCC like groups them together, and suddenly you have two R2s next to each other. Or same with the two R1s here. So like lots of options. We need a way to control for the chaos. We need to protect whatever we don't want it to react with. So our methods of protection are, for amines, we protect it by adding a Bach. And we use this Bach2O reagent. My favorite thing is like this meme, the therapist, Bach chick isn't real, Bach chicken can't hurt you. Bach chicken. Yeah. And then here for our class, we don't use the H2 palladium, we use TFA. And TFA is going to remove Bach on amine. And a student last summer made my favorite, like, dumb mnemonic for how to remember that. So do y'all know who Tina Fey is? Is like the actress, comedian Tina Fey? Is that a name that rings a bell at all? It's okay. Tina Fey. TFA. Tina Fey. Tina Fey hates chickens. So Tina Fey removes the Bach that we protect an amine with. So I thought that was a fun little, like, just in my head I have a picture of this woman, Tina Fey, just being really mad about chickens. And it works. Also, like, the tert butyls here are like chicken feet. Or someone says it also looks like wings of the little Bach chicken attacking. Yeah, this is the thing. When we don't teach you the mechanism for it, we have to come up with, like, little ways of how's this going to stick in my head, because otherwise we are up a creek. Okay, then if we want to protect a carboxylic acid, the way we do that is we turn it into an ester. So we do that either with our Fischer esterification to protect it, and then we deprotect it with NaOH and an H+ workup, or with H3O+. Okay, so we imagine have protected the things that we don't want DCC to react. Then, once we have our protecting groups on, DCC can only grab these two. We'll only get the pair we want. So we have our DCC step. And then you have to deprotect. You have to take off all the things that we just put on temporarily. The thing that's really nice about this is 1, 2, 3, 4, 5, 6 steps just come with protecting, deprotecting a DCC. So if you're doing a 10-step synthesis, 6 steps should be like easy money, because we have this framework of protect, DCC, deprotect. And you are guaranteed on either exam 2 or the final to have a DCC synthesis question. So it will be there on one or the other. And again, that should be the synthesis that you probably earn the most points on. So let's do a challenge problem. Let's do challenge problem 5, which is going to be a DCC synthesis. And we're going to do it together. Okay. Synthesis. What's the first thing that we should do whenever we start a synthesis? Let's do functional groups. So glycine, like, we do have an amine, we have a carboxylic acid. I'm just going to call her, she's fully an amino acid. Okay. What about our other starting material over here? We have an alcohol. Okay. Our product, the big thing that's standing out to me is this amide bond in the center. And that's like our peptide bond, kind of between two amino acids. So what we want is we want to have two amino acids, right? Like amino group, carboxylic acid group, amino group, carboxylic acid, but it's a little bit weird. So we have another amide over here. Okay. And if we know that we are going to be doing a DCC synthesis, we know we need two amino acids. One of them we have. The other one we have to make an amino acid. What was our plan for making amino acids? The Strucker. So what do we have to start with for the Strucker? An aldehyde, but we have on this other molecule just an alcohol. So we need to turn the alcohol into an aldehyde. What do we use? This is our redox, right? We're going from oxidation level 1 to 2. So if we're doing oxidation, what's our reagent? We gave her a round of applause. She was doing such hard work. CrO3. And here she is, again, working real hard. Okay. So we made our aldehyde. Now we can turn this into amino acid with a Strucker. So step 1, NaCN, NH4Cl. And you don't necessarily have to do the 1 on this because we're just doing one step and then writing an intermediate. But I like to think about the structure as 3 big steps, and so I just like to outline all of them. So at the end of this first step, we should have added a CN and an NH2.
Is that NH4Cl?
Yes. And it's like NH4 plus Cl minus ionic. Cool. Then steps 2 and 3 of the structure. 2, we do H3O plus. That's going to turn that CN into a carboxylic acid. And 3, we do a neutralize step. And for the purposes of our class, neutralize can mean take it to whatever protonation state you want, basically. So it's kind of just a catch-all to help us. In the lab, you would have to be a little bit more picky. So I'm just going to take it to this completely neutral version. And I should say, a little bit, this is kind of bad chemistry, because if your carboxylic acid is protonated, that means that our pH is below 5, because the pK of this is 5, which means that this would also be protonated. And so I just want to flag that I know it's bad chemistry. Let's not worry about it. Let's just worry about it, or say we worried about it. And this is going to be fine in terms of saying neutralize. Otherwise, it gets really in niche into protonation states, which I'm like, that's not the big picture. That's not what we need to be focusing on. Okay, so now we have a second amino acid. Okay, we have our 2 amino acids. Now let's figure out where these plug in. So when we made our central amide bond here between 2 of them, for the glycine side, this is definitely going to be our glycine side, and then the other one that has the phenyl ring, we can start doing some mapping. This pH and carbon, or this pH and carbon down here, right? And then we had this carbon here is the one that's connected to the amine. And then this purple one over here is what was the carboxylic acid in our intermediate. Whereas the glycine, you can basically see exactly how it maps on, right? All of these are the exact same kind of setup. So I'll do a yellow here. Is that going to be that carbon? So with this, DCC is going to be connecting which side of the glycine? The carboxylic acid side or the amine side? Yeah, because the amine side's just over here chilling, so DCC didn't touch that. So what that means is we have to protect the amine over here. So how do we protect amines? With our bok chicken.
You need to make them 2 different steps,
Yes. So when we give you 2 reagents, do not do this and then just react with one of them, put reagents here, and rewrite both of them again. Think about these are in different beakers. React with them as if they are in different beakers, and then later on you'll have a step that says combine. Okay, so we've protected our bok. I'm going to go ahead and kind of gray this one out because now it's protected. And then on the other side, if DCC grabs the carboxylic acid from the glycine, from the other one, it's grabbing the amine, right? The nitrogen. So we need to protect the carboxylic acid. So here, we're going to protect it as an ester. What's your favorite alcohol? Work. So we pop up an OET here, and we do our Fischer esterification. And now, she is protected, shut down. Are we ready for DCC? Are there any other side reactions that could happen with DCC that we don't want, or is DCC only going to be able to grab the things we want? Yeah, I think we're good. Man, the exam really left y'all a little scared. So, now what we can do is we can join them together, and I would write combine, and DCC. Just because it makes it really explicit kind of where both of these came from, the fact that we are combining them now, and that we also have to include DCC. And when we do that, let's write out the product. Now, I drew this suggestively like the product. It might take a little bit of work in your head to like rotate it. This directly goes onto here. And then the nitrogen here, I'll trace some carbons for you to make it a little bit easier. That is that. So that is that. Cool. So we've done our protection phase, we've done our combine phase, now we need to deprotect. And also in that deprotection, somehow we need to wind up an amide over here. So we could deprotect our Bock first or our ester first. Which do you want to try? Let's try it. So if we do that, we have NH2. I'm going to copy and paste all of this. And then we need to turn this ester into an amide, right? And our removal step for that is Tina Fey, TFA. She hates chickens. So now ester to amide. Does that go up or down in CAD reactivity? Down on our little chart. She's down. So we can just use our amine and pyridine. But here's where it's a little tricky. So like the amine we want is just here. If we chop this off and add an H, it's now NH3. So we could do like NH3 and pyridine. But isn't this also an amine? So what's to stop another equivalent of this molecule from coming along and forming an amide here? Like forming nitrogen here and then blah, blah, blah. NH, blah, 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 blah. OET, blah, blah, blah. I think I added an extra carbon. But the idea is the same. Like, if the choice is between this amine or this amine, you're going to get a mixture of products, right? So actually this tells me
We don't do we don't unprotect, we don't use Tina
we don't use her yet.
Fey. Yeah.
So we're going to react with the ester first, and then we'll use Tina Fey. So, and again, sometimes you just have to go down a rabbit hole of one path on a synthesis in order to get to the right answer. We're going to do another hard one together in section next week. That's the challenge problem. And like every year, just the students look so defeated after it. They're like, I never would have thought of that. Yeah, synthesis, it gets hard. It's a time. So now, because our Bock has protected this amine over here, we don't have any competition. We can turn it directly into the amide that we want. And then, as a last step, we can bring out Tina Fey, our last resort. So in total, zooming out, we had 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. We had a 9-step synthesis. But again, these syntheses are a little bit nicer because we have a framework and infrastructure on it. So, I think that's all I have for you. But hopefully we've knocked out like at least one full challenge problem, like parts of 2 other challenge problems. We did one of the hard skill builder mechanisms. And I think the piece of this week is like 15 pages total, something like that. So hopefully it won't take up all your weekend. Take some time to rest, kind of recharge. And then I will see you next week. Monday help room, Tuesday lecture. Thank you.